Hi, good morning. This is Trina here to discuss about spectroscopy. The basic principle of spectroscopy, UV visible spectroscopy, IR spectroscopy and NMR spectroscopy. So, all the study materials I have given in the course page. Here you can see the course page link is given. So first of all, you have to join with the code, then you can access all the study material. Not only the study material, all the probable questions, semester questions, and the solved problems are given there. And if you have any doubt, you can communicate with me either through my mobile number or through my email ID. So all these are given in my personal information. So the course chemistry, the subject code is CH101 for odd semester, CH201 for even semester. This course is for undergraduate BTech students. The streams are CSE IT Civil Mechanical for even semester, Electrical EC BME for odd semester. The credits are 3, contact hours 35. Weekly I will take 3 lectures. And to understand this concept, the prerequisite knowledge required, that is the 12th standard. The course objective, the students will learn the several concepts of chemistry. And about the outcome, students will be able to apply their knowledge for the identification or the determination of the structure of organic molecules using different spectroscopic techniques. Here I have given entire lecture plan so that you can understand that which topics will be covered in which day. So today it is the last module, the module 5, the spectroscopic techniques of chemistry will be started. So here you can see there is 3 lectures. So first lecture, that is the electromagnetic radiation, principle of spectroscopy, spectrophotometer, UV-VIS spectroscopy. So this part today I will tell you. So first of all, what is spectroscopy? So spectroscopy is the study of the interaction between matter and electromagnetic radiation via electron spectroscopy, atomic spectroscopy, etc. So historically, spectroscopy originated through the study of visible light dispersed according to its wavelength by a prism. So here you can see that through the prism, if the white light passes, then we get VIS colors. There are 7 colors we get. Now, if I give an example, like say you take a red flower. So what happens? The white light comes, it absorbs, and in the white light, there are 7 radiation. So all the radiation has different frequency, different energy level, different wavelength. So this material, the flower, named flower, this material absorb all the radiation except red. So it can reflect it back the red, this specific radiation. That is why we see the color. So in this way, the spectroscopy is the interaction between the electromagnetic radiation and the materials. So from the absorption or emission, we can understand that which bond is there or which material it is. So there may be, say, any electromagnetic radiation is passes through a material. So it may absorb, it may emit, or the electromagnetic radiation can transmit through the material. So here you can see the different application of the spectroscopy. So spectroscopy primarily in the electromagnetic spectrum is a fundamental exploratory tool in the fields of physics, chemistry, astronomy, allowing the composition, physical structure, electronic structure of matter to be investigated at atomic scale, molecular scale, macro scale, and over astronomical distances. So important applications arises from biomedical spectroscopy in the areas of tissue analysis and medical imaging. So all these are the application of spectroscopy. So we can use the spectroscopy in different fields. So now you look at this picture. So all these are the electromagnetic spectrum. This spectrum is the range of frequencies in the spectrum of electromagnetic radiation and their respective wavelengths and photon energies. Okay, so observe this. So here you can see that the wavelength is increasing when we move left to the right side. There are different types of electromagnetic radiation like gamma rays, X-rays, visible, UV and visible, ultraviolet rays, ultraviolet spectrum, visible spectrum. Okay, so gamma rays. Next is infrared, microwave. So for all this radiation, here we see the range is given. Here the range of frequency is given and the increasing wavelength is given. So here you can see the increasing wavelength from the left to right side. Okay, it is left to right side. It is the increasing wavelength, but decreasing energy. So here the wavelength you can see the initially it is less wavelength, but gradually the wavelength is increasing here. And for say we study for the visible spectrum, so it is ranges, ultraviolet spectrum ranges from 100 nanometer to 400 nanometer. And the visible spectrum ranges from the 400 nanometer to 700 nanometer. So it is increasing frequency in the opposite side. It is given, and increasing energy is also in this side. It is given. So here you observe if the UV rays. So we know that UV rays is harmful for us. So what type of harm it may cause? So UVB, the frequency, the wavelength range is given, that is the 280 to 320 nanometer. So this causes burning. So how it damages? Basically they damage our DNA. So by burning it damages, and the UVA, that is a 320 to 400 nanometer, this causes aging. So these are the harmful effect of the ultraviolet spectrum. And here you can observe that for the violet ray, for visible spectrum, so it is the violet and here it is the red. So VIS, first it starts from the violet and ends at the red. So for the violet rays, the wavelength is lowest. For red, red color, the wavelength is highest, that is the 700 nanometer. But for violet ray, it is 400 nanometer. But the energy level it is increasing in this direction. That means the energy level for violet, it is the higher. And for in the visible spectrum, for the red, it is the lowest. So you have understood the different type of electromagnetic radiation. And X-rays, as for example, X-rays, it is used for heart X-ray. We do, and we can see the internal organ, that if there is any fracture in our leg or not. So every electromagnetic radiation has a specific energy level, specific frequency, and specific wavelength. So now, instrumental methods for spectrum analysis. So instrumental method for spectrum analysis, first I will tell about UV visible absorption spectra. So here you can see, that is the prism, that is a prism, glass prism, and the white light when passes through the glass prism, so we get the 7 colors. So we get the 7 colors. These are starting from violet, VIS, violet, indigo, blue, green, Y, O for orange, R for red, VIS, VIBGYOR. So we get the rainbow color, the 7 different spectra. Now how it works? So this is the source of light. You can see here the source of light. And the radiation, it is going through the collimator. Now when it comes, passes through the prism, we get the rainbow colors. Now if it is monochromatic radiation, then through the slit, we get only one radiation. And when it passes through the sample, this specific sample, as per absorption, we can understand, or based on the transmittance, how much it is transmitted through this sample, we can understand that which material exists in this solution. That is the basic principle. Now I will show a video, then you will be more clear about this. Okay, so this is the basic principle how the UV visible spectroscopy works, and also the Lambert-Beer law. So here you can see the water kept. First there is the source, then slit, then prism, then another slit. It is the beam splitter, then it is the sample compartment. Then it is the sample compartment. There is 2 compartments. One is the reference cell, another is for sample cell. And at last, this is the detector. It detects the current flow and show in the computer screen. So next, how it works. First, there is the source. We get the light. So this light, the beam of light, will come through the slit. When it will passes through the prism, we get again the rainbow colors. So this rainbow color, when passes through slit, we get the monochromatic radiation, the single radiation. When this single radiation, as for example, say yellow color, so it will be splitted two parallel by the beam splitter. Then one is the reference, will go through the reference cell, another will go through the sample. So if first say there is nothing, it is the same, then we get the same electricity at the detector. So what will be the intensity? Intensity is, you assume that intensity for the reference, that is the I0, and for the sample, that is I. So if we take the ratio, so initially we get that is 100 as the intensity, that means the transmission, how much it is transmitted, it is 100%. So the intensity ratio will be 100. Next, say if we put a sample in the sample cell, any organic molecule, then what will happen? Say it can absorb the yellow light. Then the intensity of the transmitted light will be reduced. As you can see here, I reduced. So this case we are not getting 100. So here the amount is reduced. Again, we are taking the same sample which can absorb the yellow radiation more. So again, it is the light is absorbed and the transmitted light intensity decreased. So I is decreased more. So again, we are taking the ratio and plot here. Again, we are giving more, same sample more. So it is reduced more. So the ratio I by I0 reduced more. So again, we plot in the graph. So it is not the straight line, it is the exponential curve. So this curve is transmittance versus concentration. So how much the light is transmitted versus the concentration of the sample. So initially the concentration was less, gradually the concentration increases. Here we have shown that. So now, if we plot in different way, like say absorbance versus concentration. So here the Beer-Lambert law comes here. So if we express that T, the transmittance, is equal to the, in terms of concentration, it is given. But we get the graph that is not the straight line, that is the exponential line. So if we plot the same thing in terms of absorbance. So absorbance means the minus log T. T is the transmittance. So we get the straight line instead of exponential curve. So it becomes easier for us to get the next data. Let's say with a known sample, we can plot this graph. Now, after that, we take an unknown sample. Then from this graph, we will get the absorbance of the specific sample. So in this way, the UV visible spectroscopy works. So you have understood very well that how the UVB spectroscopy works. You have visualized. So to understand why compounds are colored and why others are not, to determine relationship or conjugation to color, we must make accurate measurement of light absorption at different wavelength in and near the visible part of the spectrum. So the commercial optical spectrometer enables such experiments to be conducted with ease and usually survey both the near ultraviolet and visible portions of the spectrum. The visible region of the spectrum comprises photon energies of 36 to 72 kilocalorie per mole. Ultraviolet region out of 200 nanometer extend the energy 143 kilocalorie per mole. So these energies noted above, consequently absorption spectroscopy carried out in the region of called electronic spectroscopy. So a diagram showing, now I will show a diagram of various kinds of electronic excitation that may occur in organic molecule is shown on the left. Of the 6 transitions outlined, only the 2 lowest energy ones, leftmost color blue, okay, you observe here, okay, observe this figure, the energy level is given. So it is, you know that when electron is distributed, so there is the energy level for antibonding, non-bonding and bonding. So electrons take place first bonding and bond is formed. So the 2 types of bond is there, one is sigma bond, another is pi bond. And the energy level created, that is a non-bonding, this one is bonding, sigma bonding, pi bonding, non-bonding, anti-bonding, anti-bonding. For pi electron, it is for the sigma electron. So here you can see that of the 6 transitions outlined, only the 2 lowest energy ones, leftmost, okay, leftmost you can see the 2 lowest one energy level, colored blue, are achieved by the energies available in the 200 to 800 nanometer spectrum. As a rule, energetically favored electron promotion will be from highest occupied molecular orbital to the lowest unoccupied molecular orbital, and the resulting species is called an excited state. So that is the, as per the molecular orbital theory, you can see the what is the non-bonding, what is bonding, what is anti-bonding. So these have the specific energy level. So the electron will favor the promotion from the highest occupied molecular orbital, that is HOMO, to the lowest unoccupied molecular orbital. Okay, so molecular orbital, you have to take the first that molecular lowest molecular orbital and which is unoccupied. Then in the excited state, it will be promoted. So when sample molecules are exposed to light having an energy that matches a possible electronic transition with the molecule, some of the light energy will be absorbed as the electron is promoted to higher energy orbital. So you have seen the sample absorbed, and an optical spectrometer records the wavelength at which absorption occurs, together with the degree of absorption of the wavelength. The resulting spectrum is presented as the graph of absorbance. So you have seen all these things from the video, that in the graph of absorbance versus wavelength. Okay, so these things you will get the theory here. Absorbance usually ranges from 0 to 2 and is precisely defined in the context of spectrophotometer operation. So you have seen through the video that a monochromatic light is coming and it is absorbed by the sample, and we can plot by the absorbance versus concentration of the material. Then we can understand that which material is in the sample. So if we measure the transmittance, you have seen the how much light is transmitted through the material. So few amount is absorbed and few is transmitted. If we measure the amount of transmittance, so we get the exponential graph. But if we do with the absorbance versus the concentration, we get the straight line, and that is easier for us. So here the different samples are given, so different chromophore, and the examples are given. So this is the excited state and how much energy it absorbed you can see here. So how we can identify, like say a sample absorbed specifically 171 nanometer wavelength. So we can tell that contains C double bond, C bond, double bond. If say it absorbs 180 nanometer wavelength, so we can tell that it contains triple bond. If it contains, like say, this energy level, we can say that C double bond O, this group remains. Or based on this two, like the wavelength, we can tell that which group is there. It is like NO group or which group. Or if it contains like bromine or iodine, so it will absorb the energy level, the wavelength, that is 205 and 255. So if it is 205, that is for methyl bromide, and if it is 255, then it is for methyl iodide. So in this way, we can identify that what the sample contains which molecules. Now, from the chart, it should be clear that the only molecular is likely to absorb light from 200 to 800 nanometer region are the pi electron functions. And heteroatoms having non-bonding valence shell electrons. Such light-absorbing groups are referred as chromophores. So what is chromophores? Such light-absorbing group which absorb the light in the range of, you have seen the range of 200 to 800 nanometer region at the pi electron function. They are called the chromophores. The presence of chromophores in the molecule is best documented by UV visible spectroscopy. So we can understand from UV visible spectroscopy, we can identify the chromophores. And the conjugation generally moves the absorption maxima to longer wavelengths, as in the case of isoprene. So conjugation becomes the major structural feature identified by the techniques. So now the terminology of absorption shift. So there are different terminology. So in the absorption shift, if the nature of shift, it is like to longer wavelength. If it is to longer wavelength, that is called bedochromatic. To shorter wavelength, that is called hypsochromic. To greater absorbance, that is hyperchromic. To lower absorbance, that is hypochromic. So you have learned the different application of the UV-VIS spectroscopy. Just to summarize that what are the different applications. So we can say the UV-based spectroscopy is routinely used in the analytical chemistry for the quantitative determination of different analytics. So analytical chemistry, quantitative determination of different analytes such as transition metal ions, highly conjugated organic compounds, and biological macromolecules. Spectroscopic analysis is commonly carried out in solution, but solids and gases may also be studied. So solution of the transition metal ions can be colored. So it absorbs visible light because electrons within the metal atoms can be excited from one electronic state to another. So the color of metal ion solution is strongly affected by the presence of other species such as amino, anions or ligands. For instance, the color of a dilute solution of copper sulfate, you know, it is the blue color, so is very light blue. Adding ammonia intensifies the color and changes the wavelength of maximum absorption. So we can understand easily. That is the purpose of this mixing. Organic compounds, especially those with high degree of conjugation, also absorb the light in the UV or visible region of the electromagnetic spectrum. The solvents for this determination are often water for water-soluble compounds or ethanol for organic soluble compounds. Organic solvents may have significant UV absorption. Not all solvents are suitable for use in the UV spectroscopy. Like ethanol absorb very weakly at most wavelength. Solvent polarity and pH can affect the absorption spectrum of an organic compound. Tyrosine, for example, increase the absorption maxima and molar extinction coefficient. While charge transfer complexes also give rise to colors, the colors are often too intense to be used for quantitative measurement. So we can basically by the UVB spectroscopy we can identify the chromophores, the different organic molecules. So it is used in the analytical chemistry. So if I summarize what you have learned today, you have learned that means the electromagnetic radiation, what is spectroscopy, the purpose, the application of spectroscopy, which has huge application, and you have learned the UV visible spectroscopy, its basic principle and how it works. So I have given the assignment. I hope you will be able to write all these things. So first is the describe basic principle of UV-based spectroscopy, and second one, define HOMO and LUMO. So for today I am ending my session. If you have any doubt, you can communicate with me. So thank you everyone.